Vaibhav has been working in our quantum physics group, and he's been doing measurements of elemental electron energies, base energy, for a number of atoms using a number of methodologies that are for describing this. The problem is that as you add more and more electrons and electrons around the atoms and protons to the nucleus, the electron-electron interaction becomes more and more complicated. And it's more difficult to do the calculations of the ground state energy of the electrons. And there are a number of methods. There is something called molar plecet calculations, and some people called Hartree and Fock did some changes to the molar plecet calculations to make them more accurate for larger molecules. And now even that does not go all the way through all of the blocks of the periodic table, and Vaibhav is going to explain to you what they have done and what they have found out in this area. You can go ahead and take it away, Vaibhav.
Oh, thank you so much. I think, yeah, that was a brilliant introduction. Thank you so much. And I will go ahead and continue from there. I think that got the ball rolling, so I'll just start. Can everyone see? Okay, no, that's not what I want. I do not want subtitles. Perfect. Okay, so is everyone able to see the slides?
I'll take that. Showing up well to me. I see it.
Perfect. 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 Okay. Perfect. That's great. That's great. So, first of all, welcome everyone. Welcome. My name is, of course, Vaibhav, and I am the leader and one of the co-coordinators of the quantum physics group. And if you guys have already been, or if you guys are regulars to the quantum physics presentations, most of the introduction will be the same. So, I mean, feel free to just like relax, get a drink or something, but don't spoil it for the others. So what I'm going to be presenting about today is the usage of Hartree-Fock approximations for atomic energy through STO-nG basis sets. Now, before I actually go ahead and decipher what any of that meant, I do want to provide a small view into what quantum physics is. So we have two major forms of physics. One of them is what we call classical mechanics, and the other one is what we call quantum mechanics. So classical mechanics is what we use on a day-to-day basis. So for particles, for macroscopic objects, shall I say in technical terms, those follow more concrete movement and behavior. On the other hand, when we actually get into like smaller systems, the smaller we get into like towards molecular, atomic, and subatomic systems, the behavior of particles changes because we discovered that at those scales, things behave as both particles and waves, or rather everything, later we figured out everything behaves as both particles and waves, but at our scale, the wave behavior is like so like negligible that we don't take into account. But on the quantum scale, we have to. So quantum physics is the study of things at a quantum scale, and quantum mechanics is the creation of the motion, the behavior of their motion and how they move as both particles and waves at the same time, which is what we call wave-particle duality. So as it mentions here, it's one of the two major models of the universe, apart from general relativity. And it's never been disproven, but of course it does have some unanswered questions, which I can entertain questions about those towards the end of the meeting. I'm sorry, towards the end of the presentation. So one of the most important equations in quantum mechanics is what we call the Schrödinger equation. So this was discovered by Erwin Schrödinger. And so if we, for the Schrödinger equation, we use it for, what we do is we want to calculate atomic energy. Also, by the way, guys, please check the messages as well. It's very important you do. For the Schrödinger equation, we use the Schrödinger equation to find the energy of electrons within an atom. So in technical terms, we call the Schrödinger equation a differential equation, for those who know calculus, which solves for what we call the wave function of an electron in an atom. And I'll get to what that means in a second. So first of all, let's decipher this. So the funky H there, the H with the hat, we call that the Hamiltonian operator. And that's a matrix which is the total sum of the energy of the nucleus of the atom. So the total sum of its potential and kinetic energy, the internal energy, that's what is represented as the Hamiltonian operator. Your E, on the other hand, and that's what we are also trying to solve for, that's what we call your eigenvalues, or in that's of course a linear algebra term, but in essence, that's going to be all of the energies of each one of your electrons in the atom. And your psi there, that's what we call our electron wave function. Now, as I said before, the electron behaves as both as a particle and a wave. And so to model its behavior and where it may be in an atom, the probability of its location in an atom, we use what we call the wave function. So when we put this equation and we put in our calculations for the wave function and the Hamiltonian, we can get out the energy of the electrons in the atom. And one of the major questions I've gotten in both of my previous presentations is, can we cancel out the size in the equation? And the answer is no. So when you actually do matrix multiplication, the two sides of the equation will actually yield different answers, except for very specific values of E, which in this case correspond to the specific values of the energy of the electrons. So if we sum up the Hamiltonian with the energies, we can get the total energy of the atom. Now, this is an extremely useful equation, but it doesn't offer a very concrete position of where the electron may be, because we found out that's impossible. It gives a probability of where the electron may be. And we also find out that this only works for hydrogen atoms and hydrogen-like ions, so like helium plus, lithium 2 plus, and all of that. It doesn't work for multi-electron atoms because of a phenomenon known as Coulombic repulsion. So when you get two electrons, right, in one atom, both of them have negative charge, and both of them are going to repel each other. They're going to have an electrostatic force of repulsion, which in mathematical terms, you can also call that interelectronic Coulombic repulsion. And because of that, we find that the Schrödinger equation becomes much harder to calculate. Again, for those who do know calculus, we say that the Schrödinger equation is a separable differential equation, but when we get the repulsion, the equation isn't separable anymore. So we have to use different methods. So instead of actually calculating the Hamiltonian and the wave functions and the energy, we have to approximate the wave function. And that's where we use self-consistent field methods, or for short, SCF methods. So these are computational methods that approximate psi, or the wave function. We start off with what we call a basis set. And that's like your base approximation of what the wave function may be. And then we apply calculations, recursive calculations as shown in the diagram, again and again and again, until the wave function approximation becomes close enough to what we may see in the actual atom. And that's what the self-consistent method is. It's this recursive approximation until, for a certain number of decimal places for the value of the energy of the atom, those number of decimal places stay constant. So you get the same value for those number of decimal places. And that's what we call convergence. So for our program and for our project, we have been dealing with 9 degrees of convergence. And previously, for our previous projects, we were using 14 digits of convergence. So now that we have our wave function, I'll actually come back to the basis set. Now that we have our wave function from self-consistent field method, we just need to plug it in back into the Hartree-Fock equation. Plug it in back to the Schrödinger equation so we can get our energy. Now, instead of just, now since we have multiple neutrons and protons, and we also have multiple electrons, we need to make small changes to the Schrödinger equation. So what you see on the right, that's what we call the Rutan-Hall equation. And that's a modification of the Schrödinger equation for multi-electron atoms. Your Fock matrix is the sum of the Hamiltonian that we were discussing about, which is the total energy of the nucleus, with the Coulombic repulsion between electron orbitals, which we represent by the letter G, which isn't on the diagram. But C, which is here, it says orbital coefficients, that's going to be the sum of all of the wave functions of each one of the electrons in an atom. So for helium, let's say there are 2 electrons in helium. Your orbital coefficient is going to be a sum of those 2 multiplied by some constant. That's what we call in linear algebra a linear combination. So it's going to be a linear combination of the multiple wave functions. S, which is the new addition in this, S is what we call the overlap matrix. And that takes into account when the 2 electron orbitals overlap in those regions, they are contributed to by S, your overlap matrix. And finally, instead of E here, we have epsilon. And that's going to be your eigendiagonal matrix, which basically means we're going to get a matrix, and every value on the main diagonal of the matrix is going to be, it corresponds to the energy of each electron. So in that one matrix, you're going to get the energy of every single electron at their ground state. Now, going back, so now that we have this figured out, now we can plug it back in. This is the entire thing is, of course, called the Hartree-Fock method, which I don't need to continue. I don't need to talk too much about because Dr. McMahon gave an excellent explanation of how it was discovered and all of that. But going back to our basis set, now that we already know how to use our self-consistent field approximation, we need to know how to get to them. And we need to start off with some base, hence basis set. So that's how we make the initial fundamental approximation of our electron wave function. And so there are multiple mathematical ways of doing that. So instead of using Cartesian coordinates for electron density, we tend to use polar coordinates. And towards the left, the top left image, that's what we call a Slater-type orbital. So that's a very accurate way of approximating the wave function, but it's much slower and it takes much more time to run as a program to calculate. The one in the middle, in the middle down, that's what we call a Gaussian-type orbital, or sometimes a Gaussian-type primitive. Those are much less accurate, but much faster when we run them. So instead of using one Slater-type orbital, we take multiple Gaussian-type orbitals, add them together, multiply them by a constant so that they approximate a Slater-type orbital. And this is what we call a Gaussian-type orbital basis set. So the more Gaussian types we add on to each other, the closer it's going to approximate a Slater-type orbital. And in turn, the closer it's going to approximate the real wave function of the atom. One of these Gaussian-type orbital sets is what we call the Pople basis sets, because they were first synthesized by scientist John Pople. And we also call these the STO-nG basis set. And these are what we call minimal basis sets because they use a very small number of Gaussian-type orbitals. And they add them together so that they approximate the Slater-type orbital. So directing your attention towards the graph here, the black solid line you see is your Slater-type orbital progression. And this is a graph of this is a polar graph of how the wave function would look like. And the other dotted lines you see, those are how many Gaussians we're adding up to approximate that. So in STO-nG, we're adding up n Gaussian-type orbitals to approximate an actual Slater-type orbital, hence STO. So STO-2G is the least accurate, while STO-6G is the most accurate. This diagram also shows STO-1G, which means you're only using one Gaussian type to approximate, which is highly inaccurate. So we actually can't even find public basis sets for STO-1G. These basis sets have been calculated. The wave functions, the basis wave functions, STO-nG, have been calculated for all of the atoms from helium to xenon. Beyond xenon, either the basis sets are too small to be accurate enough for energy calculation, or they simply just haven't been put in the public domain yet. So with that in mind, now for the interesting part. So all of you guys who are listening to music, you can stop now because here's where the new stuff starts. Or I suppose you could listen to music. In any case, here are our project goals. So we decided to focus specifically on one part of our Hartree-Fock because initially when we were doing our project, we had a lot of scope. We tried diversifying whatever we were trying to do so that we could select one thing for a research paper. So we looked at multiple different types of methods, self-consistent field methods, We looked at stuff beyond Hartree-Fock, which sometimes are called post-Hartree-Fock. If anyone has any interest in it, I can answer that towards the end of the presentation. And we looked at a whole, we looked at an entire assortment of basis sets, but then we finalized on our STO basis sets because they were the most thorough, they had the most elements covered, and we could do a lot more experimentation with them because the basis sets were fleshed out very, very well. So what we decided to do was first we would compute the atomic energies using PySCF. I'll be coming to that in the next slide. And so we'll be computing the energy of the atom from helium to xenon using STO-2G, 3G, 4G, 5G, and 6G, and what we call the restricted Hartree-Fock method, which is Hartree-Fock with a slight simplification, basically. Then we were going to tabulate that data and create scatter plots. So we tabulated it as atomic energy versus atomic number, which I'll be showing you guys. And then we used multiple different softwares to get scatter plots. Using these scatter plots, and this was the major purpose of what we were trying to do, we wanted to plot regressions. So these regressions would not only be approximations, they would also be predictions. So approximations, because for these, the energy calculations are used on a daily basis in organic chemistry, synthetic chemistry, biochemistry, etc., and medicine. For pharmaceuticals, it's very important. So we tried finding something where instead of having to actually calculate Hartree-Fock every single time, you can just use this regression and get out a value and just use it as a very good approximation. The other thing, of course, is prediction. We only have values up until xenon. We were wondering if we could extend the graphs until beyond that, lanthanum, cerium, towards lanthanides and the F block, and see if we could be able to thereby from there perhaps work backwards to find the basis set sometime, or someone else could use what we've done to do that. So on that note, let me introduce you guys to PySCF. Now, PySCF stands for Python Self-Consistent Field Method Library. And this, as the name suggests, it's a library with Python and C++ functions and modules that allows for a whole range of self-consistent field methods, including Hartree-Fock and a bunch of post-Hartree-Fock methods, as well as for those in the chemistry groups who do density functional theory. PySCF also uses density functional theory. Now, we are only able to use Gaussian-type orbital basis sets in this and not Slater-type orbitals, but it supports Gaussian-type orbitals really, really well. And that's what we are also exploring, right? Our STO-nG basis sets. So we decided to go ahead with PySCF for that. We used a few other libraries. PySCF itself uses NumPy and SciPy for calculus calculations and scientific display of all of the data. We used matplotlib, which is an amazing LaTeX-based, or some people say LaTeX, which is the math publishing script. This matplotlib, we used it to actually get out tables in LaTeX format. And then we also used something called the basis set exchange library. And that's basically a repository of all of like an entire range of more than hundreds of basis sets for all of the atoms available. We could just call upon data from that database, so we could use it for PySCF calculations. And so now the actual process of how we were collecting this data. So first we collected data for atomic energy in Hartrees. And if anyone has questions on that, again, towards the end of the presentation, I will definitely explain that. It's a unit of energy, by the way, and we calculated it from helium to xenon. We ran our PySCF calculations on the ASDRP cluster's Jupyter notebook, and all of our data, as I mentioned, was tabulated on matplotlib. So we got out these nice, beautiful tables, as you can see on the slide. And then we collected it and transformed it into a Microsoft Excel table. The problem with this was when we were trying to convert it from image to table, that took a very, very long time. So in the future, what we're planning to do is we will have matplotlib, but on top of that, we'll also have another library so that we'll have two tables generated. One of them, which we can actually copy and paste onto Excel, and the other one LaTeX, so we can use that for a research paper. We also ran it in batches so that not only could we split it up within our group, we could also run it very quickly and get the data just like that. So these run in a few seconds if we split it up into these batches. So helium to neon, and then sodium to argon. We ran potassium, calcium, rubidium, and strontium on its own. Then we did scandium to zinc, gallium to krypton, yttrium to cadmium, and then indium to xenon. So that covers first 54 elements. And like I had mentioned before, what I'm going to be doing through this is I'm going to be taking the example of STO-6G specifically for the data to show you guys how it may have looked. As you can see, the data table here, this is the indium to xenon data table for STO-6G energies. So we have your elements there, which correspond to atomic number, and then you have the atomic energies there in Hartrees. Using this data, now that we put it in Excel after doing our image to text conversions, we put it into Excel and we got out scatter plots. From here, we actually used 3 different softwares in order to ease regression building and scatter plot building. So we used Excel. We used another software called Logger Pro for the actual regression building. And then finally, we used Desmos for the actual regression building and changing, because most of our graphing towards the end was done on Desmos because it gave the easiest, the graph clarity was the best. You could magnify and see the graph and manipulate it and all of that. And it was just much more like the user interface we felt was much easier for us to use. We used multiple different regression equations and models, as you can see on the image here. So this is from Logger Pro. We experimented with we tried more than 7 or 8 different types of regressions. We tried exponential, sine, cosine squared. We did inverse exponential, which is like 1 minus e to the power of x. And we also tried quadratic. The reason we tried quadratic was because there is an approximation of the total energy of the atom that can be proportional to the square of the atomic number. So we tried approximating like that, seeing how it worked, and we just went ahead from there. From all of these, we decided to choose 3 to actually put onto Desmos so we could more efficiently just deal with these 3 and use them, because they were also the most accurate generally. These were exponential, e to the power of x, sinusoidal, so we chose sine to the sine x in this case, and then quadratic, x squared. We put in the data for the first 36 elements onto Desmos, so then we and onto Logger Pro, so we could get the scatter plot and then build our initial regressions. And what you see here is the correlation, the R squared value for all of these initial regressions. As you can see, your sinusoid and sinusoidal and quadratic regressions are generally much more reliable and fit the data better than our exponential. In our future trials, because of a few suggestions we're also thinking of trying hyperbolic trigonometric functions for the regression. So that's something I will be coming to later. Now for, of course, the most important part, the discussion of the observations and the inferences. So what we did now, after we got all our regressions, is that we put in data from element 36 to 54. So recapping, we started off a regression from helium to krypton, that is 1 to 36. Now we're putting in data from krypton to xenon, that's from 36 to 54, and we're seeing if the regressions still fit. That is, do they still have the predictive power that we expect them to have? If we see that there isn't a major change in the, or rather if the reliability or the R squared coefficient is still more or less the same or still very good and close to 1, then we could conclude that the model does reliably fit the data. But if it doesn't, then that means that the model that we created did not fit the regression that we were creating. It does not fit the data that we had in the scatter plot. So what we did was we tried this for everything from STO-2G to 6G. I do actually want to stop sharing my screen just for a second so I could share Desmos, because I feel that may be a bit more interesting for you guys to see as well. There we go. Is everyone able to see my Desmos screen now?
Yes, we can.
Perfect. Okay, perfect. So what you see here is what we initially did. So again, STO-6G. What we did was the red dots here are the data, there are scatter plot. Then we put in our 3 regressions, which Desmos has created for us. We have e to the power of x, sine of x, and then x squared. And then we plotted them. We got our initial R squared value, and these green dots you hear, that's what we call a residual, and that's the error between the actual data set and the prediction. So as you can see, the residuals are actually quite minimal, very close to 0 when we start off. Then we add in the data from 36 to 54, and this happens. So we see that compared to our data set, your e to the power of x graph here in red, that has a negative bias, a very high negative bias. So 0.8367 negative bias. And then the other two graphs, that is x squared and sine, both of them have positive bias. So they're going upwards, right? But in all of the cases, in all of the basis sets, we had a constant, this sort of idea where our e to the power of x had a very high negative bias, but the other two had slight positive biases. The problem is we did find disparity in how these were happening, because for some of the basis sets, like as you can see in the presentation, STO-6G, STO-5G, and all of that, there's a very clear, you know, sinusoids and quadratics are much better for those compared to exponential. And then we also got others like STO-2G and 4G, where all three of them are comparable. And this is now that we have all of this data, we have to make the inferences from what what we can do from here and what we need to do. The first thing is, one of the major problems I think we face and we want to fix is that when actually when checking if the regression, when we're validating it, we actually have to manually type in the values for the A, B, and C coefficients. If like for an equation A e to the power of x plus B, we have to manually type in those values when we're putting in the actual validation of our regression. So that takes a lot of time. It's prone to error. And plus, when it's doing Desmos, also makes approximations. That is one of the things we saw when they're making the regression. The numbers it gives out isn't the actual value. So when we use those numbers, we will get some differences. So we wanted to still, decipher why there may be some disparities in all of these, in all of the validation regressions that we're seeing. We wanted to make regressions where we use all 54 elements, and so we'll make the regression, see how that compares to the one with just 36, and see where there may have been error, because in some of them they're actually quite similar, in some of them they're very different. So we have to see if maybe it is a regression program error or any of that sort. The second thing we wanted to do with a lot of suggestions is we wanted to try other regressions. So hyperbolic and trigonometric regressions, hyperbolic trigonometric regressions, I'm so sorry. So that's sinh and cos of x. We were planning on using those and seeing if that worked. And like I had mentioned, most of these, the one that has like physical theoretical basis, because there needs to be one in science. It's not like kind of like in statistics where you can just choose a model and see how it works. You need to also have physical basis when creating a regression. You can't just use a random one. And the one we thought would be the closest or the best regression that's physically, hinted at is x squared, the quadratic one. And the reason being, when we can represent the energy of an atom as the sum of the energy of the nucleus with the energy of its electrons. So the energy of the nucleus is represented by the Fock matrix, and then the electron energy, we can approximate it using something called the Rydberg equation. Now, I'm not going to get too much into detail into either of those two, but the problem is, in short, the problem is neither of those two have like a closed form, as we say, because you can't write them algebraically, but you can approximate them as being atomic energies directly proportional to the atomic number squared. So that's why we tried our quadratic function, but we want to explore more and to see if there are better approximations. The third thing that comes up, and this I think will guide our project towards the end as well for our future goals, it may be that we have encountered a null hypothesis or a null result, where it's actually impossible, since there is no closed form to represent the energy in terms of atomic number, there may be no regression that is suitable enough. In terms of approximation, yeah, a lot of them were good in terms of approximation for the first 54 elements, I'm sorry. But for prediction purposes, we have right at this point of time come to the conclusion that all of the models we tried out, none of them are suitable enough because of very low R² values for approximations and extrapolation of the regression to other elements beyond xenon, so the lanthanides and the actinides and all of those. And of course, with all of these, we plan to get out a research paper by the end of May or the beginning of June. And that brings us to almost towards the end of the presentation. I won't keep you holding for much longer. The future goals for our presentation. So first of all, we wanted to try out the other SCF methods. Like I was mentioning before, we wanted to try out beyond Hartree-Fock. There are multiple other methods. As Dr. McMahon mentioned, one of them was Moeller-Plesset, but a better version of it called Moeller-Plesset perturbation theory. There's one called configuration interaction. There's another one called coupled cluster. All of these basically take Hartree-Fock and change a few errors that are present in Hartree-Fock, which were discussed in the previous two presentations. So I would encourage you to go ahead and check those videos out as well on the YouTube channel. And we were also planning on observing other basis sets. So we wanted to look at, to see what we call the CCPV-NZ basis sets. So these are also Gaussian types, but the way they approximate is different. So these sets are much bigger. In terms of, when we say bigger, we mean the more Gaussian orbitals are added up. So these sets are much bigger, and their approximations are usually much better for atoms as well and atomic energy. So we wanted to check if we could use these and see if we could create a progression for the elements. And also there are some specialized basis sets for each block. So if we look at a periodic table, there's a section in the middle, we call that the D block, and the section all the way at the bottom, we call that the F block. Now those, when the electrons actually join the atom in those blocks, they don't join what we would call the valence shell or the outer shell. They actually join inside, and they join another orbital inside that isn't on the valence shell. So when we create basis sets for them, or like wave function calculations, we have to use specialized basis sets specifically for the D and F block. So we are planning on investigating how those work. The last thing for our future goals is we were also thinking of maybe potentially pairing up with the quantum computing group. And they have been, of course, working on some really exciting stuff with molecular geometry, like synthesizing molecular geometries with quantum computing techniques. So we were thinking of maybe collaborating with the quantum computing group and using those molecular geometries to calculate energy, seeing if that not only to strengthen the QGAN, the neural network for the molecular geometry synthesizing, but also so that we can investigate on theirs and take our project from not only an atomic level, but move to the next level, which is a molecular level, calculating energy for molecules and their bonding properties and all of that. And with that, I will conclude the presentation. The last few things, I would like to give credit to everyone that made this possible. Dr. McMahon, and of course, he was our advisor, and he's the one who guided us and made sure we actually came to the meetings and did work and everything, and made sure we attended Colloquium as well. And so he has been a great help, and we have to give him a lot of the credit for everything we're doing. ASDRP, of course, that gave us our the platform to do the research, and all of our group members. I've listed the current group members here, but honestly, everyone, the current and past group members, everyone's been working so much on this. So without any of the work, we wouldn't have been able to come where we are. And I would also like to mention Mr. New Edward and Diptanshu, because both of them gave us a lot of advice on how to proceed and other things, like maybe small things we were missing out and errors that we saw here and there and how we can proceed forward. So with that, I will finish, and now I'm open to questions. Actually, you know what? I have one question before we start. I was unsure if, so all of the data I presented were only for STO-6G. I do have the data as a QR code towards the end for all of the other basis sets. So I was wondering if I could just show that as well, or if that would be against like ASDRP's intellectual property if I show the QR code with all of my data. Or
I think you should ask your advisor.
Sure.
Yeah, and I don't know like how small is going to be because when you scan the QR code, you need a cell phone, right?
Right.
I mean, yeah, and then they get a QR code and direct it to data, like the link to the data or the actual data. So it's going to open in their phone, like.
Right. So, yeah, actually, that was a great question. So the data is actually on a Google Drive. I've just organized everything on a Google Drive. So so it's a link to the Google Drive. So if they scan it, people scan it via iPod or like iPhone or something, they can just scan it and they'll be redirected to the Google Drive where they can actually see all of the process of the graphs that we created and all of that.
Yeah, that will be interesting to look into. Great presentation, Vaibhav. But I have a couple of questions for you that regarding your data analysis.
Sure.
You multiple times you talk about the scatter plot.
Right.
Where is your scatter plot?
So the scatter plot here is actually, it's hidden by the, oh, so I'm so sorry. So it's actually hidden by the regression. So what you see there, the dots there, that's actually the initial scatter plot that we see for that. This is of course atomic energy versus atomic number, but because of the other graphs, the dots, the purple dots that you see at the bottom, they're actually being obscured. Those were our initial scatter plots. As opposed to
you know what is the word scatter means, right?
Right.
So I do not categorize this graph at all as a scatter plot. I mean, scatter plot.
Let me jump into that. A scatter plot is any time you are plotting a bunch of XY values without not trying to draw a contiguous line, just plotting the points. If you run a regression on those, you can find that the scatter plot may actually wind up being on a curve. The word scatter is you're taking it in a slightly different meaning. The scatter means that it's a bunch of individual points. It's not a curve drawn, but you can draw regression lines through it.
As opposed to, although of course I can see why something confusion would pop up, because in a lot of scatter plots, the reason it's called a scatter plot is because there is no curve at all or no regression. So all of the plots are
No, hold on a second. You can't, the scatter plot are the set of points that are presented from the through the X and Y. Right. So they're scattered all over. They can be a positive correlation through the scatter plot. It can be negative. There can be no correlation, or it can be basically nonlinear. Right,
exactly.
So, and then you find the pattern, you find the correlation. These dots are very, very nicely aligned, and I mean, is just representing to me nice overfitted nonlinear curve regression plot.
Right. Perfect.
So
okay. I would like to jump in here at that point. Overfitted is a overstatement, so to speak. We found a bunch of points, run a regression on it, and you get the best fit possible. It's not like you are trying to okay.
PCF.
Basically, I do not understand your criticism. All right.
Dr. McMahon, I'm not able to hear you. I think there's some audio feedback.
Okay, can you hear me now?
Ah, perfect. Right.
Yeah, there was somebody else that came on with an open mic.
Ah, sure. Okay.
So I think the issue of a scatter plot having to look scattered is a fallacy.
Yeah. It would in certain cases, but like, I mean, like, I can see in a lot of economic stuff and like statistics for that sort of things, scatter plots do look scattered in that case. But when we're dealing with like something although these do count as scatter plots, they're not like, of course, they may not seem like the traditional definition, but exactly like what Dr. McMahon said, you can still have like these sort of nonlinear curves and all that.
Yeah, I mean, I agree. You know,
in the future,
worked for years as a data analyst for years, and you know, I work with multi-dimensional data. I don't know how many data points you have, but I can see these numbers are absolutely close. And you try so many models, exponential, sinusoidal, quadratic. What is it saying to you? It's saying that these models are absolutely close and nonlinear, and what you can see through that, based on my experience, if I publish a paper and pass it to the journal, the first thing that they see that they said that, okay, this is overfitted data visually by those numbers, looking at those numbers, because it's just, you know, it is when you do regression, you try to find what data fits best. But what I can see, there's a graph that data is nicely fitted into, you know. So we publish paper, we send to the reviewer, they get back to us. It's just, this is how it is. This is just how we interpret this kind of graph. It's not like I have my own definition of scatter plot. I'll be like, you know, there's something like, you know, saying that the color of water is blue, or it's dark blue or purple blue or whatever. It's just, there's something called as default. And when you want to see a scatter plot, you want to see a scatter plot. These are just very nicely nonlinear pointed into assembled into a graph. So I don't know what you call it, but this is not scattered. I mean, you go and start reading any statistical book, just Google search a scatter plot, you will see what does it mean. These points are absolutely, you can see from numbers how close from each other. That means they already have some pattern in it. You're not scattered, you're not finding any regression through this. Yeah, so I don't know.
One of the
I am not very, you know, with wording, I'm not very comfortable, like how statistically you are putting this as a scatter plot. I would not.
No, if there are definitely, I mean, I do see that there are definitely some disputes over the wording, because one of the things we were doing is an approximation. So I can see where the overfit comes. We can definitely, I'll definitely go ahead and I'll look at that. The first thing I do will be to look into that and I'll see how we can change it, and definitely I'll incorporate that as well.
Okay.
Thank you so much.
So the other thing is, at this point, Sahar, you and I have been monopolizing the questions. We should try and find out if there's anyone else here who would have questions about this. Don't think it's too far over your head. I know some of this was some fairly heavy quantum physics, but there must be some questions that you have about this. Let's see if we can get some feedback from some of the other participants. If you don't want to speak up, feel free to type it in chat.
Sure, that's a great idea. Let's hear what.
Like Dr. McMahon said, yeah, a lot of the, okay, wait, hold on, before I continue talking, Satya has a question.
Yeah, can you hear me?
Yeah.
Okay, so this is going to be building off of Sahar's question a little bit. So even through maximum parsimony, if the data is overfitted, you guys try linearizing it? Like, for example, for the exponential, you try taking the natural log of the y's, or for the quadratic, taking the square root, and then finding r squared?
So doing a linearization. So that is actually one thing we have planned. We haven't done it yet as such, but yeah, that's a great point. We are planning on linearizing it as well. I should have mentioned that. Really sorry about that. We are linearizing. We're planning to do that next, but exactly, we haven't done that as of yet. Although that is one of the things we are looking at doing as well. Most likely what we're going to be doing out of all of the data sets, we're going to be linearizing the quadratic one, because that's the one which we, like I said, has your physical basis. We're trying to see if there is actually the physical meaning as well, where we can actually relate atomic numbers squared to energy and see if that works out. So that's the first one we will be looking at and spending much more extensive research on doing. But yeah, exactly.
And I'd like to add a few words to why he keeps bringing up the physical basis. You can get a very close approximation with a number of these he's found, obviously. But if you can find something that there is a model that points to the physical coordinates of everything and the way that the things are going, what he's saying is that there are other models for behavior that go with the square of the number of electrons. And so if a quadratic model works, it helps to make a connection between the other model and this model.
And so the other models in question, the other two models that we're dealing with, one of them is a quantum physics model. The other one actually is one based on algebra. So that's why we're trying to find the physical meaning that, like both Dr. McMahon and I were talking about. We want to see if maybe our Hartree-Fock based group theory based abstract algebra model does somewhat agree with both the calculus models and the algebra models that have been presented in history, which namely, respectively, they're the Hartree-Fock, the Schrödinger equation and the Rydberg equation for the electrons.
Okay, I see. And then really quickly, second question. So from my understanding, like I thought R squared was the variability accounted for in the response in a linear model, right? So how were you guys interpreting R squared for non-linear models? Does it work differently for quantum models or?
So R squared is actually a statistical thing which you can use for linear models. There's a slightly different way of calculating R squared, but at the end you actually get the same result. So your R squared, of course, is kind of, again, same thing. It's the variance of the data with respect to your actual regression. And that is the same for any graph you choose. For any data set, you can look at the variance and calculate an R squared value for that. But as you mentioned, there are slight differences between the R you see in linear data and the R squared you see for any other sort of regression. But the R squared value if you calculate it by both ways for linear models, they should be more or less the same. Just that there are different equations to calculate the two values. But yeah.
Okay, I see. Thank you so much.
Of course.
Next person. Okay, thank you very much, Vaibhav, and thank you, people, for coming to the thing, and I hope you enjoyed the presentation.
I did get, sorry, one last question. Just wondering how big are the matrices, like the Hamiltonian ones? Those are quite big. Those can get very, very large. Those can get up to like 100 elements on each side. Plus, the Hamiltonian, you actually get them from a differential equation. So the way it works is that for different equations, you actually get different sizes, but in essence, they're very big. I'll keep it at that. Thank you, everyone, and that concludes my presentation.